data center provider in Germany and want to improve your CO2 footprint. Data centers make up somewhere between 1 and 3% of the global power consumption, and according to the IEA, are expected to have roughly the same electricity demand as Japan by 2026. Therefore, they usually produce a sizable amount of emissions, and many data center owners have made pledges or already made investments to reduce those. In today's project, we will model a data center near Essen, Germany, that will go from a normal retail tariff to investing in solar PV, a battery, and lastly, an agreement with an optimizer to allow assets to be aggregated for market trading. Let's have a look at how we can model this in GridCog. We will run our model over a period of 25 years with a discount rate of 2% to account for inflation. For our baseline, let's choose a fairly stable load with total energy consumption of 4.7 gigawatt hours and a maximum demand of around 1.1 megawatts, representing our data center. The electricity retail tariff is attached to the site meter. Let's assume the data center owners are paying 13 cents per kilowatt hour on a flat tariff, which includes network tariffs. We also have an asymmetric grid connection limit of 2 megawatts for import and 1.8 megawatts for export. In the second scenario, let's add solar PV, trialing 3 sizes, 1, 2 and 3 megawatt peak. The solar will feed the load and export at a set tariff of 9 cents per kilowatt hour whenever there is any excess solar generated. In the participants and value flow section of the software, we can assign the revenues and expenses of our data center owner. In the third scenario, let's assume that the data center owner also invests in a small battery system with 2 size variations, 500 and 1000 kilowatt hours. By ticking both self-consumption and co-optimize, we can have a look at how the battery revenues will vary based on its strategy. Self-consumption means our battery will only charge from the solar and discharge into the load. Co-optimized means the battery will react to price signals and operate in an optimal way to serve load and maximize revenue. Finally, let's create a fourth scenario where the battery is optimized and traded into wholesale and ancillary markets by an aggregator or optimizer. For this scenario, we will also have a look at larger battery sizes. In the participants and value flow section of the software, let us now add another participant, the optimizer, who will keep 15% of the wholesale and ancillary revenues. Once the simulation has finished running, we can have a look at the results. Let's start in the Load Shape Analysis tab. We can see how grid import, marked in blue, shrinks with more and more solar PV, which is marked in yellow. We can also use this tab to analyze the difference between the non-optimized and the optimized battery in scenario 3. The battery state of charge is the purple line, and in the self-consumption variation you can see that it only charges from the solar PV peaks and discharges immediately after. When changing the settings to co-optimized, we can see that the pattern is now very different. The battery charges from solar and discharges overnight to reduce dependency on the grid. In the Project Options Overview tab, we can sort all our variations by internal rate of returns and have a look at which of the modeled options might be the most attractive. GridCog helps you decarbonize your behind-the-meter site with CapEx investments that allow you to save money long-term.